Hello students, welcome to the third video of chapter 5, 5C. This is a continuation from the previous video where we were talking about half-lives. So half-lives of some radioisotopes are shown in this table along with the type of radiation that it emits. As you can see, we have some medical isotopes, naturally occurring radioisotope. The half-life, for instance, of carbon-14 is 5,730 years versus carbon-11, which is 20 minutes. Chromium-51 is 28 days. 6 hours is for technetium-99. Radon at 222, 3.8 days, etc. 2 minutes is for oxygen-15. So all of these are examples of naturally occurring radioisotopes, some of the medically recurring medical radioisotopes, and as you can see, the naturally occurring have a large half-life, versus the medical radioisotope, which have a lot smaller half-life, and that's basically because you want the radioisotopes to be removed from the body. You don't want them to stay in the body, and so for that reason, the radioisotopes that are used in medical applications have a short half-life. Now, if we take a look at this problem right here, it helps us to understand how we can do some half-life calculations. The radioisotope strontium-90 has a half-life of 38.1 years. So half of that radiation would decay in 38.1 years. If a sample contains originally 36 milligrams of SR90, how many milligrams will remain after 152.4 years? So the question here is a word problem. We need to do some calculations. The first thing, let's go ahead and write our given or unknown. Our given is that we have originally 36 milligrams of SR90. It has a half-life of 38.1 years. We need to know how much of it is left after 152.4 years. So taking a look at our given and unknown, let's go ahead and set up a plan. Well, from the number of years, I can convert that to half-lives. That's going to help us some way, you'll see. And then milligrams of SR90, I need to convert it to milligrams remaining. How do I do that? Let's go ahead. If I know that one half-life equals 38.1 years, so therefore 152.4 years, how many half-lives is that? So I use this conversion factor, the conversion factors in one of these conversion factors right here, and to convert years to half-lives. So this is a representation of 4 half-lives. Well, let's go ahead and write it down. Originally I have 36 milligrams. After the first half-life, I'm going to go down to half that amount, which is 18 milligrams. 2 half-lives, 18 will go down to half the amount, 9 milligrams. 3 half-lives, 9 milligrams will go down to 4.5 milligrams. 4 half-lives, the half will go down to 2.2 milligrams of SR90. So basically I have 2.2 milligrams left of SR90 after that amount of time. Here's another question. Carbon-14 was used to determine the age of the Dead Sea Scrolls. If the Dead Sea Scrolls were determined to be 2,000 years old, and the half-life of carbon-14, which was used, the radioisotope that was used, is 5,730 years, what fraction of this half-life has passed? So this is a question asking asking for a different thing. Let's go ahead and type down what we have. 2,000 years old is our given for the piece. C14 half-life is 5,730 years. How much of that fraction has passed? Because 2,000 is less than 5,730 years, so it has to be a fraction. So the first thing that we do in our plan is to convert years to fractions of half-life using the half-life conversion. One half-life is equal to 5,730 years, so 2,000 years times one half-life over 5,730 years will give us 0.3. So 0.3, or almost, let's say, 30% of the half-life of carbon-14 has passed so far. Another question here is asking about, so the half-life of iodine-123 is 13 hours. How much of a 64 milligram sample of I-123 is left after 26 hours? Very much like the first question that we just looked at. Let's go ahead and type our given or unknown. 26 hours is the time that we have. The half-life is 13 hours. Original amount is 64 milligrams. So go ahead and write a plan. So we have hours, we need to convert those to number of half-lives, just like what we did before, and then we convert the milligrams into how much remaining. So one half-life is equal to 13 hours. Now, if we have 26 hours, that equates to 2 half-lives. So you convert it using the conversion factor coming from the half-life equation, equivalency, and that adds to half-life. So originally, if I'm starting with 34, after the first half-life, so after 13 hours, the amount will drop down to 32 milligrams. 32 milligrams have decayed, and I have 32 remaining. After another half-life, after another 13 hours, the 32 milligrams will decay down to 16 milligrams, etc. So the correct answer is B. Now, here are some examples of medical applications that use radioactivity. We've all heard of radioactive iodine that is used for thyroid scanning, for the scanning of your thyroid. This is a radioactive isotope that enhances the image, it provides contrast, and it helps in medical diagnosis. So radioisotopes with short half-life, as we saw in that previous table, are the ones recommended to be used because you don't want that radioisotope to remain in your body for a long time. The cells in the body do not differentiate between non-radioisotope atoms and radioactive atoms. Once they incorporated into the cells, the radioactive atoms are detected because they emit radiation to give an image of the organ, and that's how they assist in the imaging. Here are some examples of radioisotopes that are used along with their half-lives. Scans with radioisotopes. After a radioisotope is ingested by the patient, after they give you the radioisotope and you take it, the scanner will move slowly over the organ where the radioisotope is absorbed to detect an image. So the radiologist determines the level and the location of the radioactivity emitted, and that helps in the medical diagnosis. Now, gamma rays emitted from radioisotopes can be used to expose a photographic plate, which can really produce a scan of the entire organ. Here's a scan of a thyroid gland using I-131. Now, we've heard of PET, we've heard of a CT scan, MRI, all of these use certain types of radiation. PET, for instance, uses positron emitters. It can be used to study the brain function, metabolism in the body, blood flow, and it might be carbon-11, oxygen-15, nitrogen-13, or fluorine-18. What they emit is a positron. If you remember, this is what the positron looks like. So they combine with electrons after the emission to produce gamma rays, which are then detected by computers. And this is what creates a 3D image of the organ. This is an instance of a PET image of a brain affected with Alzheimer's disease on the right and a normal brain on the left. As you can see, there are some variations in the image detected. A CT scan, or what we call computed tomography, is another imaging method that uses X-rays, and it monitors the absorption of 30,000 X-rays directed at the brain in successive layers, and it is used for imaging the brain, the lungs, the heart, and for instance, in this image right here, it shows that there is a tumor. And why do you see that there's a yellow color here? Is because there could be differences in absorption of the X-rays based on tissue density and fluid that is in the image, in the structure. So if there's differences in density, you'll see a different color. Or if there's differences in the tissue absorption, you'll see different colors. MRI is the imaging technique that does not involve any X-ray radiation, and it's least invasive because it involves a magnetic field. This magnetic field causes the hydrogen atoms in the body, which are present in water molecules and other carbohydrates molecules in the body, other essential molecules in the body. What it does is that it excites that hydrogen atom that starts to rotate as a result of the electric field. So the energy is basically that is absorbed, it is converted to color images, and there's a lot more into this, but we're not going to go into specifics of MRI, but it uses a magnetic field. Here's an image for the heart and the lungs of a patient. Here's a sample question that involves asking you which of the following radioisotopes are most likely to be used in nuclear medicine. One that has a half-life of 1.3 times 10 to the power 9 years, 12 hours, or 8 days. Of course, in my opinion, a medical doctor would not like you to have a radioisotope in your body for that long of a time, such as the option A. So therefore, B and C are possible options. They will be likely used because of the short half-life. Now, as we have all heard of brachytherapy some of us have, or not all. It's called brachytherapy, and what it is that it's a seed implantation, and it is used in the treatment of different types of cancers. What happens is, in that process, there's an implantation of 40 or more titanium capsules, and they're called seeds. What they do is they utilize radioactive iodine, palladium, or cesium in the seeds to decay by gamma emission, and that gamma emission will destroy the cancer cells by interfering with their genetic makeup, their reproduction, and by, of course, trying to cause as minimal of damage as possible to the surrounding tissue. Temporary brachytherapy is used in prostate cancer in males, and what it does, it implants long needles containing iridium-192 into the tumor, and that's done in real time. It can be used to deliver high amount or high dose of radiation over a shorter period of time, and then it can be repeated after multiple days. The needles are then removed 5 to 10 minutes, depending on the activity of the isotope. This is how temporary brachytherapy is done. Permanent brachytherapy is the one that involves implanting seeds in the malignant area where the tumor is. Thank you very much for your attention. Have a blessed week. If you have any questions, please let me know, and I look forward to hearing back from you. Blessings, you all.